Hello students, welcome to my YouTube channel Datasha. In today's lecture, we'll be talking about the degenerate solutions in the linear programming problem. So we know that we have a basic solution. So there are two kinds of basic solutions. The first one is the degenerate and the other one is the non-degenerate solution. So what is a degenerate solution and a non-degenerate solution? A non-degenerate solution is the one in which none of the basic solutions is 0, and on the contrary the degenerate solution is the one where at least one of the basic solution is 0. So in today's lecture we'll be talking about such example where we'll be having the degenerate solution. So how we can handle it and what would be our solution. So there are certain conditions when the degeneracy occurs in a linear programming problem. So in the linear programming problem, degeneracy may appear in the following two ways. The first one, when some component of bi is equal to 0. So if we are having the bi's, that means in the given question, the right hand side of the constraint, if any of those are equal to 0, then obviously you will be having a degenerate solution as the final answer. Second condition is if none of the bi is 0, but the minimum ratio that we are finding for the leaving variable, there is a tie, so it is not unique. In that case also we have a degenerate solution in our linear programming problem. So let's consider this example. Maximize z is equal to 3x1 plus 9x2 with the two constraints we have. Now as this is less than equal to constraint, so we know that we have to add the slack variables. So I can rewrite the linear programming problem as, so in the standard form it would be maximize z 3x1 plus 9x2 subject to the constraints x1 plus 4x2 plus s1 equal to 8. So with a 0 cost, and x1 plus 2x2 plus s2 is equal to 4. Again it with a 0 cost in the objective function, where x1, x2, s1 and s2 are all greater than equal to 0. So s1 and s2 are the slack variables that we have. So when we will be applying this simplex method, we will be getting such kind of a table where the basic variables are s1 and s2. So first thing that whenever you will get you will write your linear programming problem in the standard form, then the second step is we have to find out the basic solution. So the basic solution is s1 is equal to 8 and s2 is equal to 4, and I have written it here. The cost associated with them is 0. Now write down all the coefficients ai's in this area. So z is coming out to be 0, 0 into 8 plus 0 into 4. Cj is mentioned above. Now when we calculate a delta j, that is zj minus cj, so we'll be getting this. So automatically we could see this is the most negative, so this is the entering variable, and in this when we'll find out the leaving variable, you will notice that we are having a tie here. So this is 2 and this is 2. We could take s1 also as a leaving variable, and we can take s2 also as a leaving variable. So this will give us a degenerate solution. So this is how we can identify whether we'll be getting a non-degenerate solution in our LPP or a degenerate solution. So we could take anything in this. So I'll be taking both the cases. So let us consider the first case, case 1, where I'll be taking s2 as my leaving variable. So this is the entering variable and this is my leaving variable. Now with this my pivot element is this. So in the next iteration table, S1 would remain as it is, Now x2 is entering and s2 is leaving, so 0, 9. This would be, I have to divide the whole row by 2, so this becomes 2, half, 1, 0, half, and this would be row 1 goes to row 1 minus 4 times of row 2, so 8 minus 8, that becomes 0. This is 1 minus 4 by 2, so that's minus 1. This becomes 0. This is 1 again, this is, and 0 minus 4 by 2 is minus 2. So calculating z is coming out to be 18. Zj is 9 by 2, 9, 0, 9 by 2. And delta j, that is zj minus cj, so 9 by 2 minus 3, this is coming out to be 3 by 2, this is 0, 0, 9 by 2. So I am getting all of the delta j's as positive, so that means I have attained the solution here. So what is my solution, the optimal solution that I am getting? So the solution is that x1 is equal to 0 and x2 is equal to 2. So this is what I am getting here. X2 is equal to 2. So when you will substitute here in this, we'll be getting the answer, the maximized z. You could also get it from here that it is coming out to be 18, and also the objective function that we have was 3 times x1 plus 9 times x2, so that's 3 into 0, 9 into 2, that's 18. So the same we are having here, the solution. So z is equal to 18. So this is how we have obtained seen the case 1 where I have taken s2 as my leaving variable. Let us consider the second case where I'll be considering s1 as my leaving variable. So this would be the leaving variable and this is the entering variable. So now the table would be x2 will enter, s2 will remain, so this is 9, 0. So now the pivot element is this, so I have to row 1 divided by 4, so I have to make it 1, 2, 1 upon 4. Row 2 must be 0, so row 2 minus twice of row 1, so this would be 0. 4 minus 4 is 0. 1 minus half is half, 0, this is minus half, just the same, and this is also 1. So z is coming out to be again 18. Zj is all positive that we are getting here. So delta j is 9 by 4. So this was 9 by 4 minus 3. So 9 by 4 minus 3 is minus 3 by 4. So we are getting a negative term here, and this would be 9 minus 9, 0, 9 by 4 minus 0, and this is 0. So we'll be taking this as our entering variable, and what will be the leaving variable we can decide. This would be 2 upon 1 by 4, that's 8, and this is 0 we are having here, so this is 0. So this is the leaving variable, and the entering variable would be x1, so s2 is the leaving variable, and this would be our pivot element. So we would be making another table. So here it would be x2, x1, so this would be 9, 3. Now the other values I have not created the table, never mind, I'll just do it here only. So I have to make it 0, so this would be 0, 1, 1, 0. So the row transformation, row 2 goes to twice of row 1, row 2, and this would be 0, 0. that's minus 1, that's half, and row 1 would be row 1 minus 1/4 of row 2. So I'll be getting the answers as 2, 0, 1, half and minus half. So let's quickly find out what is our ZJ. ZJ, if you'll notice, we are getting it as 3. This is 9. This is 9 by 2 minus 3. So that's 9 by 2 minus 3. So that would be 3 by 2. This is minus 9 by 2 plus 3 by 2. So that's minus 7 by 2. So delta J, if we'll see here, let me just write the delta J's here now. So 3 minus 3, it becomes 0. 9 minus 9 becomes 0. 3 by 2 is again the same. This is not negative. I think I have not written it correctly. Let me just, this is 2, sorry. So minus 9 by 2 plus 6 would be 12 by 2. So this is coming out to be 3 by 2. So all are positive, as we could say, see here. So what is the solution that we are getting? So the solution that we are achieving here is x1 as 0 and x2 as 2, and maximize z is again 18, right? So here you could identify the same. X2 value is coming out to be 2, x1 is coming out to be 0, and z, if we'll calculate it is equal to 18. So the answer doesn't change, but yes, we are getting a degenerate solution here, and similarly in the first case also. So this is the degeneracy in the linear programming problem, and in the next one we'll be talking about the unbounded solutions.